Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from limits, right? And in this session we are going to discuss this limit, that is limit x tends to 1, x raised to 5 minus fifth power of greatest integer of x divided by x raised to 4 minus fourth power of greatest integer of x, right? So in this class we'll see whether the limit of this function involving the greatest integer function it exists when x tends to 1 or not, right? So for the existence of limit of a function, what we have to do, we have to separately find out the right hand limit and the left hand limit, right? And we see whether the right hand limit exists and it is finite. Similarly, we see whether the left hand limit exists and finite, and if right hand limit is equal to the left hand limit, then we claim that the limit of the function at the given point it exists, right? So let us examine the limit of this function when x approaches to 1 by finding out the right hand limit and the left hand limit. So let us take this function as f of x, right? And the notation for right hand limit is the limit x tends to 1, and here we write a positive sign, and here we have f of x. So here we have x is equal to 1, and when we approach from x is equal to 1, from the right of x is equal to 1, then we reach at a point which is very close to x is equal to 1, and this point or this neighborhood may be taken as 1 plus h, right? And similarly, when we find out the left hand limit, we approach towards x is equal to 1 from the left of x is equal to 1, right? And we take a point in the left neighborhood of x is equal to 1, and this point may be taken as 1 minus h, right? So 1 plus h is obviously greater than 1, and 1 minus h is less than 1, right? So now we'll take x is equal to 1 plus h, right? And here this quantity h is infinitesimally very small, and it lies between 0 and 1, right? So when x tends to 1, then h tends to 0, right? So now the right hand limit can be written in terms of h as the limit. Here we have h tends to 0, and here we have f of x. X is 1 plus h, right? Okay, so now let us find out the value of f of 1 plus h by replacing x by 1 plus h, right? So we have x raised to 5, so here we have 1 plus h raised to 5. Then we can have greatest integer of 1 plus h raised to 5, and here we have 1 plus h raised to 4 minus greatest integer of 1 plus h raised to 4, right? So now we have to evaluate this limit when h approaches to 0, right? Now see, here we have greatest integer function. So first we have to take care of this greatest integer function, because greatest integer function is a very special function, and whenever we come across with this greatest integer function in limits, then we cannot directly substitute h is equal to 0 over here, right? So what we will do, will apply the definition of greatest integer function here. So see, 1 plus h, here we have greatest integer of 1 plus h. So 1 plus h, because h is a very small quantity, right? So uh, when we add h to 1, then 1 plus h is slightly greater than 1, but it is always less than 2, right? So it means 1 plus h, it lies between these two integers 1 and 2. And from the definition of greatest integer function, we can say that greatest integer of 1 plus h should be equal to 1, right? Because 1 is the greatest integer less than 1 plus h, right? So now greatest integer of 1 plus h may be replaced by 1. So here we have a limit h tends to 0 and 1 plus h raised to 5 minus 1 raised to 5, and here we have 1 plus h raised to 4, and here we have 1 raised to 5, right? And 1 raised, here we have 4, so this is 1. So we have limit h tends to 0, 1 plus h raised to 5 minus 1. And here we have 1 plus h raised to 4 minus 1, right? So now we have to evaluate this limit, right? So we have already got rid of this greatest integer function by taking greatest integer of 1 plus h as 1, right? Okay, so now to solve this limit, we have a variety of methods, but here we'll make use of the famous L'Hopital's rule, right? Because see, when we take h is equal to 0 in the numerator, we have 1 plus 0 is 1, 1 raised to 5 is 1, so we have 1 minus 1. And when we take h is equal to 0 in the denominator, then 1 plus 0 is 1, 1 raised to 4 is 1, and here we have minus 1, so this is 0 over 0, right? So we get the 0 over 0 form in this limit, so we can easily apply the L'Hopital's rule by differentiating the numerator and denominator separately with respect to h, right? So now we have the derivative of 1 plus h raised to 5 minus 1, and here we have the derivative of 1 plus h raised to 4 minus 1, right? Okay, so now the derivative of 1 is 0. Here also derivative of 1 is 0. So the derivative of 1 plus h raised to 5, by making use of the power rule for differentiation, we have 5 1 plus h raised to 4, right? And by chain rule, the derivative of 1 plus h is simply 1. And here in the denominator we have 4, derivative of 1 plus h raised to 4 is 4 1 plus h, and here we have 3, 4 minus 1 is 3, and then the derivative of 1 plus h by chain rule is 1, right? So we have 5 over 4, 5 over 4, and here we have the fourth power of 1 plus h, here we have third power of 1 plus h. So cancelling the common powers here, we are left with simply 1 plus h, right? So here we also have the limit notation, right? Here also we have the limit notation, right? Okay, so now we can take here h is equal to 0. So limit h tends to 0, 5 by 4 times 1 plus h is 5 by 4. And here we have 1 plus 0. So this is simply 5 over 4, right? So the right hand limit of this function when x approaches to 1 is given by 5 over 4. Now let us find out the left hand limit. So now we have the left hand limit as LHL, and this is limit. Here we can write x tends to 1, and here we put a negative sign, and here we have f of x, right? So when we calculate the left hand limit, we take x is equal to 1 minus h, as we have already explained here. So we have x is equal to 1 minus h, right? So when x tends to 1, then h tends to 0. So now the left hand limit is limit x tends to 1 minus may be replaced by h tends to 0. And here we have f of 1 minus h, right? So now the value of f of 1 minus h can be obtained by replacing x by 1 minus h. So we have 1 minus h raised to 5, and here we have greatest integer of 1 minus h raised to 5, and then we have 1 minus h raised to 4 minus greatest integer of 1 minus h raised to 4, right? Okay, and here again we have the same situation. We have the greatest integer function, and we cannot directly substitute h is equal to 0 over here, right? Okay, so now we'll make use of the definition of greatest integer function. So this quantity 1 minus h, because h is positive quantity, right? And when we subtract h from 1, then this number is slightly less than 1, but it is greater than 0, right? Okay, so 1 minus h, it lies between 0 and 1, and the greatest integer of 1 minus h is equal to 0, right? Because the greatest integer which is less than 1 minus h is 0. So now here we have limit h tends to 0, and we have 1 minus h raised to 5, and here this quantity is 0. So we have 0 raised to 5, that is simply 0, and here we have 1 minus h raised to 4 minus 0 raised to 4. So now we have limit h tends to 0, 1 minus h raised to 5, because this is 0, this is 0, and 1 minus h raised to 4, right? So now here this term get cancelled. Here we are left with only the 1 power of that is 1 minus h. So we have limit h tends to 0, 1 minus h. So now we can take h is equal to 0. So this is 1 minus 0, that is 1, right? So here's the left hand limit is given by 1. So we can see that the right hand limit and the left hand limit both exist, right? So here both the limits exist and they are finite. But the important thing is that right hand limit is not equal to the left hand limit, right? So these two limits are not equal to each other, because 5 by 4 is not equal to 1. So we can say that the limit of this function when x approaches to 1, it does not exist, right? So the limit of this function when x tends to 1, it does not exist, because the right hand limit is different and the left hand limit is different, right? So for the existence of limit of a function at a given point, both the limits must coincide, right? And moreover, both the limits should be finite. Hello viewers, in today's session we are going to discuss another important and conceptual problem from limits involving the signum function and greatest integer function, right? So here we have to discuss this limit, that is limit x tends to 2, and here we have the signum function of greatest integer of x minus 2, right? So here the square brackets denotes the greatest integer function. So here we have to see whether the limit of this function when x approaches to 2, it exists or not, right? So for this, what we will do, we'll find out the right hand limit and the left hand limit. So let us start. So now we know that for the existence of limit of a function at a given point, both the right hand limit and the left hand limit should be finite, and both these limits should exist, right? And moreover, if the limit of the function is to exist, then both these limits should be equal to each other, right? So first we'll find out the right hand limit of this function, right? So let us take the function f of x as signum of greatest integer of x minus 2, right? We'll also define the signum function, and here we have the right hand limit. The notation is limit x tends to 2, and here we put a positive sign, and here we have f of x, right? So here we have x is equal to 2. So when we find out the right hand limit, then we approach towards x is equal to 2 from the right of x is equal to 2, and we take a point in the right neighborhood of x is equal to 2, and this point is 2 plus h, right? And when we find out the left hand limit, then we approach towards x is equal to 2 from the left of x is equal to 2, and we take a point in the left neighborhood of x is equal to 2, and this point is 2 minus h, right? So when we calculate the right hand limit, then we take x is equal to 2 plus h, and this quantity h is a positive quantity, and it lies between 0 and 1, and h is infinitesimally very small, right? So when x tends to 2, then obviously h tends to 0. So now we can express this limit in terms of h. So we have limit h tends to 0, and here we have f of x, and x can be replaced by 2 plus h. So now f of 2 plus h can be obtained by replacing x by 2 plus h in this function. So we have limit h tends to 0, and we have signum of greatest integer of 2 plus h minus 2. So now we can write limit h tends to 0, and here we have signum of greatest integer of h, because this 2 and this 2 get cancelled, right? So now we have to find the value of greatest integer of h, and we have already said that this quantity h, it is infinitesimally very small, but it is positive and it lies between 0 and 1, right? So from the definition of greatest integer function, we can see that when h it lies between 0 and 1, then the greatest integer of h should be equal to 0, right? Because the greatest integer of h that is less than or equal to h is this number, that is 0, right? So here we have the greatest integer of h as 0. So now we have limit h tends to 0, and we have signum of 0, right? So now we can omit this limit sign here, so we can simply write signum of 0, and we know the definition of signum function, that is signum of p is defined as plus 1 whenever p is greater than 0. Signum of p is 0 whenever p is equal to 0, and signum of p is minus 1 whenever p is less than 0, right? So here we see that the value of p is 0, so signum of 0 should be equal to 0, right? So the right hand limit of this function f of x when x approaches to 2 is given by 0, right? Now let us find out the left hand limit. So the notation for the left hand limit is given by limit x tends to 2, and here we put a negative sign, and here we have f of x. So now we take x is equal to 2 minus h, because in this case we are approaching towards x is equal to 2 from the left of x is equal to 2. So all the values of x should be less than 2, right? And when x approaches to 2, then h tends to 0. So now writing this limit in terms of h, we can have left hand limit equal to limit h tends to 0, and here we have f of x, x is 2 minus h. So now we have limit h tends to 0, and f of 2 minus h can be obtained by replacing x by 2 minus h. So we have a signum of greatest integer of 2 minus h minus 2, and now this 2 and this 2 get cancelled, and we have limit h tends to 0 and signum of greatest integer of minus h. So now here we have a signum of greatest integer of minus h, and we have to first write the value of greatest integer of minus h. So what we will do, will make use of this inequality, that is lies between 0 and 1. So multiplying this inequality throughout by minus 1, we have 0. The direction of the inequality get reversed, so we can now write minus 1, then minus h, and then 0, right? So minus h lies between minus 1 and 0, while h lies between 0 and 1. So the greatest integer of minus h should be equal to minus 1, right? So now the left hand limit is given by limit h tends to 0. We have signum of minus 1, right? Now since this term is independent of h, so we can now remove this limit notation. So we have simply signum of minus 1. Now see, we have defined signum of p as minus 1 when p is less than 0. So here p is minus 1, which is obviously less than 0. So signum of minus 1 is equal to minus 1, right? So the left hand limit is equal to minus 1. Now we can see that both the limits, that is the right hand limit and the left hand limit, both exist and they are finite. But these two limits are not equal to each other. So the right hand limit is not equal to the left hand limit because 0 is not equal to minus 1. So we can say that the limit of this function when x approaches to 2, it does not exist.